Hello and welcome to Balliol College Online. This is one of the Insight into Maths series, and today we're going to learn about representation theory with Aurelie.
So hello everyone, my name is Aurelie, and I thought I'd just give you a brief introduction about my academic background. So I did my undergraduate degree in mathematics and physics in France. So I did a double major in maths and physics, and then last year I came to the UK to do my master's in mathematical and theoretical physics in Oxford, and I specialized in theoretical particle physics. And then this year is my first year of DPhil, or a PhD, in the mathematical physics group in the Maths Institute in Oxford. And I'm going to start sharing my slides. So hopefully everyone can see my slides, and I'll perhaps make this a bit smaller. And I also thought that before starting the session, I would like to say that representation theory is quite an advanced topic that you could be expected to be taught in third or even fourth year of undergrad. So in my case, I first saw representation theory last year during my master's. And what I hope to do today, my aim is really to give you an idea of what representation theory is and why we're interested in studying it. I'm aware that quite a few of the concepts that I'll introduce are quite abstract, and I really don't want you to worry if even by the end of the session there are some notions that still seem a bit unclear. I really hope to give you at least an informal idea of really the main concepts in representation theory, really what it is and why we're interested in studying it. So then I'm going to start by motivating representation theory. And of course, I should start by telling you what representation theory is. So representation theory is a field of mathematics concerned with the study of abstract algebraic objects using their representations on vector spaces. So I'm aware this definition might seem quite abstract, which absolutely it is, and so I'm going to walk you through the definition. So we really have three key concepts here. We have the abstract algebraic objects, which are the objects that we're interested in studying. We have their representation, and we have vector spaces. And these are the three concepts that in my motivation slides, I want to introduce to you in an informal way to give you really the conceptual idea of what they are, and then I'm going to move on to define these concepts more formally. So I'm going to give you their mathematical definition. But so let me start then informally by giving you an idea of what they are. So on the one hand, you have a type of object, abstract algebraic objects, which are the objects that we're interested in studying. And then on the other hand, you have another type of object called a vector space. And then representations are what allows to link the two. It is what allows the abstract algebraic objects that you want to study to have an action, and to be even more precise, to have a linear action on this other type of object called a vector space. And that is how representation theory allows you to study abstract algebraic objects. It allows us to study these objects by considering the action of the abstract algebraic objects on vector spaces, the linear action of these objects on the vector spaces. And that's really what I hope to show you in the diagram below. So on the one hand, you have the abstract algebraic objects that you're interested in studying, like a group or an algebra. Then on the other hand, you have this other object called a vector space, and then in between, your representation is what allows your abstract algebraic object to act linearly on your vector space, and this in the end is what allows us to study the abstract algebraic object. So then, let me start by telling you a bit more about abstract algebraic objects. So an abstract algebraic object is just a set For example, this could be a set of numbers like the real numbers or the integers. And on this set, there is one or several bilinear operations defined. So what a bilinear operation is, it is just some operation that takes two elements in the set, and it acts on each of these elements in a linear way. So to give you examples, if you consider the integers and addition, addition is a bilinear operation on the integers. So it takes two integers and adds them together. You can't just have one integer and add it. You do need two integers. And on each of these integers, it acts in a linear way. So that is what an abstract algebraic object is. It is a set together with one or several bilinear operations defined on the elements in the set. Now, onto the other object that is relevant in representation theory, vector spaces. A vector space is just a set whose elements are called vectors. So the elements in a vector space are called vectors. And on these vectors, there are two operations defined called addition and scale multiplication. So you can see some kind of analogy between the abstract algebraic objects that we want to study and the vector space. In both cases, we have sets. And for the abstract algebraic objects, we have at least one bilinear operation defined on that set. And in the case of vector spaces, there are two operations defined on the set, namely addition and scale multiplication. And finally, we have representations which allow the abstract algebraic object to act on vector spaces. And more precisely, a representation is just a function that takes elements in your abstract algebraic object. So this object could be a group or an algebra, and your representation is a function that takes an element in your algebraic object and associates to it a specific type of function called a linear function or a linear map. So map and function are just synonyms. So your representation takes an element in your algebraic object and it associates the specific type of function called a linear function, which acts on a vector space. What that means is that your linear map takes an element in your vector space, so it takes a vector, and it associates another vector in your vector space. And that is how your representation allows your algebraic object to act on your vector space. It takes an element in the algebraic object, it associates a function, a specific function, which is a linear map, and which takes an element in your vector space, a vector, and gives back another vector. And so now, why are we interested in studying representation theory? So, as I was telling you, what we are interested in doing is studying abstract algebraic objects. So we are interested in studying a problem in abstract algebra, studying an abstract algebraic object. And as the name indicates, this algebraic object can be quite abstract, so quite difficult. It might be quite difficult to study that algebraic object, and in some cases we might not even have the tools to study that abstract algebraic object. But what representation theory does, remember, is that we consider so rather than studying our abstract algebraic object, the representations which act on the algebraic object take the elements in the algebraic object and associate linear functions which act on a vector space. And as the name indicates, these functions, these linear functions, are linear, and so they can be studied using the formalism of linear algebra. So linear algebra is just this formalism in mathematics which allows to study problems that are said to be linear. And such problems are just problems that are defined by linear equations. So the equations are said to be linear. And this is much, much easier than studying problems in abstract algebra. So really, representation theory allows you to transform a problem in abstract algebra, namely studying an abstract algebraic object, into a problem in linear algebra. Because what it does is that rather than forcing you to study the elements in your algebraic object, it allows you to study instead the linear maps that are associated by the representation to the elements in your algebraic object. And these you can study using linear algebra. So really, representation theory allows you to drastically simplify the study of abstract algebraic objects, and in some cases it might even make it possible, whereas in the first place you might not have had the tools to do it. And to give you an idea of why we would even be interested in the first place in studying these abstract algebraic objects, I'm going to give you an application, and here I am a bit biased, I'm going to give you the physics application. So a key stake in physics is to construct physical theories with specific symmetries. As an experimentalist, you would study an object or a system in your lab by performing experiments, and you would get results of these experiments. And then what you want to do as a theorist is to construct a physical theory that would explain the results that you get when you perform your experiments. And now, if when you perform your experiments, you observe that your system or your object has a symmetry, for example, this could be mirror symmetry, then when you construct your physical theory, you want your physical theory to have that symmetry. So you want to impose in the construction of your theory that the theory obeys that symmetry, because otherwise it wouldn't be a good theory to explain the results that you get when you do your experiments. So, as a theorist, what you want to do is to construct physical theories with specific symmetries. And in order to do that, you need to know how your symmetries act on the basic building blocks in physics, which are vectors. For example, in classical mechanics, you study an object, you know that you have some forces which are applied on that object, and then you want to know where will my object be later. So you want to study the trajectory of your object. To be more precise, what you do is that you study the evolution in time of the position of your object. And the position of your object is just a three-dimensional vector. So it is a vector with three components, the x, y, and z components of the position of your object. If later in your undergraduate degree you go on to study general relativity, you will see that instead of considering three-dimensional vectors, we now consider four-dimensional vectors, because you also consider a time component. So the first component is a component which depends on time, and then you have the x, y, and z components of position. So to construct your physical theory with specific symmetries, you need to know how the symmetry acts on basic building blocks in physics, which are vectors. So you need to know how symmetries act on vectors. And that is on the physics side. Now, mathematically, a symmetry is associated with a group. And if you remember from the previous slides, a group is just a specific type of algebraic object. And since you want to know how your symmetry acts on vectors, mathematically, you need to know how your group acts on vector spaces, which are just spaces whose elements are vectors. But then hopefully you remember this is the whole point of representation theory, to study the action, the linear action of algebraic objects, which in particular could be groups on vector spaces. So in physics, to construct your physical theory with specific symmetries, you need to use and study representation theory. So really, representation theory is a key mathematical subject within physics. And finally, before moving on to giving you the formal definitions of the concepts that I've introduced to you, I hope with this diagram to illustrate how your algebraic object acts on your vector space. So you start with your algebraic object, such as a group or an algebra. And in this algebraic object, you take an element, small g. Your representation is a function, which we denote by r, which takes this element small g, any element small g, and associates r of g, which is a linear map acting on vectors. It is a linear map acting on a vector space. And because this linear map is the result of applying a representation to the elements in our algebraic object, we call it a representation map. So your representation map is the linear map that you get when you apply your representation R to the elements in your algebraic object. And this representation map belongs to what we call the general linear group of a vector space. This general linear group is just by definition the set of linear maps that act on the vectors in the vector space. So your representation map, it takes a vector small v and it acts on it and it gives you back another vector R of g of v in your vector space. And that is how your algebraic object acts on your vector space. The representation acts on an element small g in your algebraic object and gives a linear map R of g, which is called a representation map. And this representation map takes a vector small v in your vector space and gives back another vector R of g of v in your vector space. And now when I give you the formal definitions, I'm going to restrict to the representation theory of groups, meaning that rather than considering any abstract algebraic objects, I'm going to only consider groups. And you have two types of groups. You have finite groups and continuous groups, and this will give you two different kinds of representation theory of groups. You have the representation theory of groups of finite groups and the representation theory of continuous groups, which are a bit different in that they don't use the same tools, let's say. And representation theory of finite groups is a bit more straightforward. Representation theory of finite groups, so finite groups are groups whose, so the number of elements in the group is finite, and continuous groups, which are also called Lie groups, are groups which, in addition to having the mathematical structure of a group, are also something that we call a differentiable manifold. And without going into the details, a differentiable manifold is just a space that can be arbitrarily complex, but if you zoom in enough on that space, then it really looks quite simple. So really, it needn't be simple, but if you zoom in enough, it looks very simple. And so now I'm moving on to defining to you mathematically what a group is. So a group is a set G. So usually we'd call it G, but truly you can call it anything. So it's a set together with an operation which we call multiplication, which goes from G Cartesian product G into G. So here I want to emphasize that we call the operation multiplication and we write a small dot, but truly it could be any type of operation. It could be addition, for example. It could also be multiplication, but it really could be any type of operation. But to give it a generic name, we call it multiplication. And so it goes from G Cartesian product G into G, which means that it takes two elements in G. That is what the Cartesian product means. And it gives you back a single element in G. And so that is what a group is. It is a set together with an operation which we call multiplication, and these satisfy three axioms. So for the first axiom, if you take any three elements, G1, G2, and G3 in your group, then whether you first multiply G2 by G3 and then multiply the result that you get by G1, which is what you are doing on the left-hand side of the equality, or whether you're first multiplying G1 by G2 and then multiplying this by G3, then it doesn't matter. So you get the same result independently of which order you choose to multiply your elements in. So in words, the order in which you multiply your element is irrelevant. You get the same result in the end. And this property is just called associativity. So that is the first group axiom. It is that the operation should be associative. Now for the second axiom, it requires that in your group you have an element E, which satisfies E times G is equal to G for any element small g in your group. So essentially what the equation says is that if you have any element small g and you multiply it by E, then you get back your small g. So multiplying by the element E doesn't do anything. You just get back your element. And that is why we call the element E neutral element. So your second axiom requires that your group has a neutral element. And finally, for the third axiom, it is that if you take any element small g in your group, then there should exist an element g prime, which is also in your group, and which depends on small g, and such that the equation g prime times g is equal to E. So multiplying g prime and g gives you the neutral element. And here I want to clarify that what the axiom says is that choose any element small g in your group, then there exists another element, which could actually be the same, g prime, which is also in your group, and this g prime depends on g. And when you multiply the two, you get the neutral element. And this is not the same as saying that there exists some element g prime in your group, such that whichever other small g that you choose in your group, g prime times g is equal to E, is satisfied. No, because so we don't have one element such that you multiply it by any other element and you get the neutral element. No, the g prime really depends on the small g. So you start by choosing any small g, and then there exists a g prime which depends on this small g, and such that the equation is satisfied. And this element g prime is called inverse element. And what the third axiom requires is that you do have such a g prime for any small g in your group. And so that is what defines a group. A group is just a set together with an operation which we call multiplication and which satisfy these three axioms. And I do want to emphasize also that you should always specify the operation on your group. So really a group is a set together with an operation. It is not just a set, because you could consider a same set and different operations on that set. So really, when you talk about a group, you need to specify the set and the operation. And now, depending on the nature of the operation, you have two types of groups. You have groups that we call commutative or abelian, so these two words are synonyms, and groups that are non-commutative or non-abelian. So groups that are commutative or abelian are those for which the operation is commutative. So the operation being commutative means that if you take any two elements, G1 and G2, then G1 times G2 equals G2 times G1. So it doesn't matter in which order you multiply your elements, you get the same result in the end. And so when your group is commutative or abelian, the operation on the group is commutative. And to give you some examples of commutative operations, if you consider the integers and addition of the integers, then the addition is commutative, because it doesn't matter in which order you add your integers. For example, 2 plus 3 is equal to 5, but 3 plus 2 is also equal to 5. Now, to give you a counterexample, you might all be familiar with matrix multiplication, at least if the matrices are of size 2 by 2. If you take two matrices, A and B, which are different, then in general, A times B is different from B times A. So here, matrix multiplication is not a commutative operation. And to give you examples of groups that show you that you really are familiar, you've already encountered these groups, you just probably haven't been told that they have the mathematical structure of a group. Here I've included the example of the integers together with addition, they form a group. Similarly, if you take the rational numbers together with multiplication, they also form a group, or the real numbers together with addition also form a group. And so let me show you why, prove why the integers together with addition form a group. So we need to verify that the three axioms on this slide are verified. So for the first axiom, addition on the integers is indeed associative, because if you have three integers and add them, then it doesn't matter if you first add the first two, or if you first add the second and the third, you get the same result in the end. So addition of the integers is associative. Now, for the second axiom, neutral element, the neutral element for the integers together with addition is 0. And here, really, it is important to specify the operation because the neutral element depends on the operation on your group. So you could have different neutral elements depending on which operation you're considering. And the same holds true for the inverse. The inverse also depends on the operation that you consider. But so when you consider the integers with addition, the neutral element is 0, because if you add 0 to any integer, then you just get back your integer. And finally, any integer has an inverse for addition, which is just minus the integer. For example, minus 3 plus 3 is equal to 0, and 0 is indeed the neutral element of the integers. So here I've, at least with words, proved to you that the integers together with addition indeed forms a group. And in particular, the three examples I have on this slide are commutative groups because the operation is commutative, so addition and multiplication. And now that I've defined to you what a group is, I can define what the maps on groups are, so the functions that go between different groups. These functions are called group homomorphisms. So a group homomorphism is a map or function f which goes from some group G into another group G tilde, and this group homomorphism satisfies the equation in the red box. And that equation says that if you take any two elements G1 and G2 in your group G and you consider the product G1 times G2, and you then apply your group homomorphism f, so what you get is f of G1 times G2, then what you get is the product of f of G1 and f of G2. So in words, the image of a product in G is the product of the images in G tilde. So here, if you're not familiar with this terminology, the image of an element by a function is just what you get when you apply the function to that element. And this holds for any, it doesn't have to be a group homomorphism. So you have some element x and you have a function f, then f of x is the image of x by f. And so here in the case of group homomorphisms, if you consider a product in G, G1 times G2, and you apply f, what you get is the image by f of your product. And this is equal to the product of the images of your individual elements. So f of G1, the image of G1 by f, multiplied by f of G2, the image of G2 by f. And now for some special types of group homomorphisms, if your group homomorphism f is bijective or invertible, then we call it a group isomorphism. If your group homomorphism is such that it goes from a group G into the same group G, so in your definition of a group homomorphism, G tilde is equal to G, then we call it a group endomorphism. And finally, if your group endomorphism is bijective or invertible, then we call it a group automorphism. And now, if you do study maths at university level, you'll probably discover more and more that mathematicians are quite sloppy, and quite lazy when it comes to terminology sometimes. And so rather than talking about group isomorphism, group endomorphism, group automorphism, we'll just talk about isomorphism, endomorphism, and automorphism. So once you have a group G, you can consider the set of automorphisms of that group G. So this is just the set of invertible endomorphisms on that group. And this forms a set. And if on that set you consider an operation which is called composition of maps or composition of functions. So this is just it. So composition of function consists in applying functions successively. For example, if you have any functions, which don't have to be group homomorphisms, if you have two functions f and g, then f composed with g means that you first apply g and then you apply f. So if you consider the set of automorphisms of some group G together with this operation called composition of maps, then this forms a group, which we call the automorphisms group of G, and which we just denote by aut G. And now for a quick introduction to vector spaces. A vector space is some set E, again we could call it anything we want, together with two operations on that set, which we call addition and scalar multiplication, and together they form a list of axioms. That is just what a vector space is. A set together with addition and scalar multiplication, and they satisfy some axioms. And here, addition means that you are adding two elements in your vector space. So you're adding two vectors, since the elements in your vector space are vectors. Scalar multiplication is a bit different. It doesn't mean that you multiply two vectors in your vector space. It means that you multiply a vector in your vector space by a number. And to give you examples, again, you are all familiar with vector spaces, although you just probably don't know that they have the structure of a vector space. If you take the real numbers together with addition of real numbers and multiplication of real numbers, this forms a vector space. And this is a specific example in which addition and multiplication, the scalar multiplication, are just usual addition and multiplication of real numbers, since addition consists in adding two elements in your set, so in your real numbers, so you add two real numbers, and scalar multiplication here consists in multiplying an element in your set, so a real number by a number. So in this specific case, scalar multiplication is just the normal multiplication that you're used to. But if I now take another example, the real plane, so the set of two-dimensional vectors with real components, together with addition and scalar multiplication, this also forms a vector space. And in this case, we are not talking about the same addition and multiplication. Here, addition is addition of two-dimensional vectors, and scalar multiplication is multiplying one two-dimensional vector by a number. And finally, I'm going to give you the most trivial example of a vector space. If you just consider the number 0 and you consider the set which just has the number 0, and you consider this set together with addition and multiplication of real numbers, this also forms a vector space, which we call the zero vector space. And once you've defined a vector space, you can consider the functions that act on that vector space. And these functions are invertible linear maps. So they are a specific type of functions which are invertible and which are said to be linear. And linear just means that they satisfy the equation in orange. And what that equation says is that if you take two vectors x and y in your vector space, so if you consider the vector space of the real numbers, x and y would be real numbers. If you consider the vector space of the plane, x and y would be two-dimensional real vectors. And if you consider the zero vector space, then you have no choice but to choose x is equal to y is equal to 0. So x and y are two vectors, and if you multiply x by any arbitrary number lambda, so lambda here just is a constant that could take on any value, and you multiply y by some other number mu, which again, mu could be any number, and then you add the two together. So you consider you get a big vector, lambda x plus mu y, and then you apply your linear map, your linear function, then what you get is lambda f of x plus mu f of y. So lambda multiplied by f of x added to mu multiplied by f of y. So that is just what a linear map or a linear function is. It is a function which acts on a vector space and which is linear, meaning that it satisfies the equation in orange. So once you have a vector space, you can consider the functions acting on the vector space. So the functions acting on the vectors in the vector space. This set is the set of invertible linear maps acting on the vector space. And if on this set you consider composition of functions, which is the operation that I introduced to you earlier, then this forms a group, which we call the general linear group of the vector space. And finally, now I can move on to defining formally to you what a representation is. So remember that a representation enables the action of an algebraic object, and here I'm considering a group, on vector spaces. And to be more precise, it allows the algebraic object to act linearly on the vector space. Mathematically, what a representation is, so the representation of some group G on a vector space V, it is a group homomorphism, R, which goes from the group G into the general linear group GL of V of the vector space. So it takes an element small g in your group and it associates R of G, which belongs to the general linear group of the vector space. So that means that R of G is an invertible linear map acting on your vector space by definition. So R of G, we call it a representation map, and it is just a linear map acting on the vector space V. And here I just want you not to be confused by the fact that when we talk about the representation of a group on a vector space, we do talk about, so when we consider the representation R, we talk about the representation of a group G on a vector space V. But truly the representation itself goes from the group G not into the vector space V directly, but it goes into the general linear group of the vector space V. So it goes into the group of linear maps which act on the vector space V. So that is what your representation is. It is a function that takes elements in your group and maps them to linear maps, which we call representation maps R of G, which act, as the name indicates, linearly on V. And once you have a representation, you can associate to that representation a number which we call the dimension of the representation. And the dimension of the representation, we set it to be equal to the dimension of the vector space V. Now, the dimension of a vector space V, it's a number, and I'm just going to consider finite dimensional vector spaces. So you have some vector spaces which are infinite dimensional, meaning that their dimension is infinite, where I'm going to just consider finite dimensional vector spaces, the vector spaces that have a finite dimension. And so the dimension of a finite dimensional vector space is equal to the number of vectors in the basis of your vector space. And the basis of your vector space is just the set of vectors such that any other vector in your vector space can be expressed in terms of these two vectors, or these, any number of vectors. And I said two because I'm going to give you the example of the plane. If you consider the plane with whose elements are the plane vectors, then any vector in the plane can be expressed in terms of the unit vector along x, so the vector 1, 0, and the unit vector along y, so the vector 0, 1. And so in your basis for R2, you have these two vectors. So the two unit vectors, the unit vector along x and the unit vector along y, are the two elements in your basis. They form the basis of R2. So the basis of R2 has two vectors, and so that means that the dimension of R2 is 2. And now, if you were to consider the representation of some group on R2, your dimensions would be two-dimensional, since they have the same dimension as the vector space R2. And now that I defined what a representation is, I'm going to define the two types of representations. So we have irreducible representations and reducible representations. So irreducible representations are the building blocks of representation. So they are the simplest type of representation. They can't be decomposed. On the other hand, in contrast, reducible representations are those which are composed, you could say, of the irreducible ones. So you obtain reducible representations by doing some operations on your irreducible representations, like, for example, adding them together. And you, to illustrate this to you, you can see an analogy with fractions. Fractions, you have irreducible fractions and reducible fractions. So irreducible fractions are the simplest possible fractions, those that can't be made simpler, those that can't be decomposed. And we're always interested when we talk about fractions to give the irreducible fraction, because the reducible fractions are somehow a redundant description of your irreducible fraction. If you consider, for example, a cake and you ate half the cake, then what's relevant is that you ate half of the cake. So you ate 1 divided by 2 of the cake. You wouldn't say that you ate 5 divided by 10 of the cake or 10 divided by 20 of the cake, because these are just redundant ways of saying that you ate 1/2 of the cake. And here, when it comes to representations, it's really the same. When we study representations, we're only interested in the irreducible representations, which are the simplest ones, because the reducible ones we can always just find by doing operations on the irreducible ones. For example, coming back to fractions, 5 divided by 10, you can obtain it from 1 divided by 2 by just multiplying both numerator and denominator by 5. And so what a reducible representation is, if we consider a representation R of some group G on some vector space V, then it's said to be reducible if there exists a vector subspace U of your vector space V. So here a vector subspace, it's just a kind of smaller vector space in your big vector space. And if the representation R is reducible, then there exists such a vector subspace U, which satisfies the equation in the red box, which is equivalent to the definition, the equation underneath, which is perhaps easier to understand. So what it says is that you take a vector small u in your vector subspace, and then when you apply your representation map R of G on that vector u, on any vector small u, then the result that you get, the vector that you get, is still in your vector subspace. Now, I want to emphasize that this is not necessarily the case. By definition, R of G, the representation maps, are linear maps from the vector space V into the vector space V. So the result that you get is definitely in V. Now we are choosing to consider a vector subspace and acting on that vector subspace. So rather than taking any vector in V, we consider a smaller vector space, U, a vector subspace, and apply the representation maps on this vector subspace U. But the result that you get could still be in V while not being in U, because by definition, when you apply your representation map, you get a vector in V, not necessarily in U. But so if your representation R is reducible, then there exists at least one vector subspace U, such that if you apply your representation maps on the vectors in U, then what you get, R of G of U, is still in U. And that is exactly what the equation in the red box says. It says that if you apply R of G on your entire vector subspace U, so you apply it on every single vector in U, then you get a space which is a subspace of U. So it still belongs, the elements still belong to U. And if such a U exists, we say that it is invariant under the action of the group. Because remember, the action of the group on the vector space, it consists in applying the linear maps R of G on the vector in the vector space. And here, when you apply the representation maps R of G on the vectors in your vector subspace U, you still get a vector in U. So the vector subspace U is invariant under the action of the group. And I want to say, kind of by default, an irreducible representation is just defined as a representation that is not reducible. So it can't be decomposed. And this is the end of my theory. I've defined the main concepts to you, so groups, representations, and vector spaces. And I thought with this example I'm going to end on, that hopefully this will illustrate all of the concepts that I've introduced to you. So the example I'm going to consider is the cyclic group Zn. So to give you the definition of the group, here I'm using the slightly sloppy mathematician notation, where you say that the group is equal to the underlying set, so the set in your group. But truly, I want you to remember that a group is a set together with an operation. But very often, if the operation is implicit, so it's kind of obvious what the operation is, you would see sometimes group equals set. But strictly speaking, that is not true. But it's a notation you'll see quite often. So the set in the cyclic group, for any natural number n, it is 0, 1 until n minus 1. So it's all the numbers starting at 0, the natural numbers starting at 0 and going until n minus 1. And the group law, so the operation defined on the set 0, 1 to n minus 1, is addition mod n. So addition, it's just the standard addition that you know, and the mod n just means that if the result of your addition is n, then you have n mod n, which is 0. So essentially the mod n just means that n is equivalent to 0. And so in mathematics, the mathematical way of writing that the group law is addition mod n is, if you consider P and Q in your cyclic group, then P times Q equals, by definition, that is what the symbol here means, the colon and equal sign. So P times Q equals, by definition, P plus Q mod n, so addition mod n. And here, don't be distressed by the fact that on the left-hand side we say times, as if it was a multiplication, and on the right-hand side we say addition. Really, as I said, times is, or multiplication is, the generic name that we give to the group law, but that doesn't mean that the group law is actually a multiplication. And your cyclic group is a finite abelian group. Finite because it has a finite number of elements, n elements, and abelian because the group law, addition mod n, is commutative. And now we're interested in the irreducible representations of the cyclic group Zn over complex vector spaces V. So don't worry too much about the fact that the vector space is complex. And these irreducible representations over complex vector spaces V are one-dimensional. So they have dimension 1. That means that the vector space V is always one-dimensional. So whichever V complex vector space V consider, it is one-dimensional. And since the vector space of the complex numbers, so the complex numbers do form a vector space, we can take V is equal to C, so the vector space of the complex numbers. So we are looking for the irreducible representations R, which go from the cyclic group Zn into the general linear group of the vector space of the complex numbers, GL of C. And this GL of C is just the entire set of complex numbers, C, except 0. And now I'm going to show you how we find these irreducible representations, because remember, we're only interested in the irreducible ones. And what also, I should specify what I mean by finding the irreducible representations. So what we want to know in the end is how our cyclic groups act on the vector space of the complex numbers. So we want to find the irreducible representations. We want to find, to be more precise, the representation maps, because they are, in the end, what acts on the vector space. So in order to find our irreducible representations R, we can just find the image of the irreducible representations R when you act on each of the elements in your cyclic group. So you want to know R of 0, R of 1, until R of n minus 1. And if you have these images, so the image of the elements of the cyclic group under your irreducible representation R, then these are the representation maps, and they fully specify the irreducible representation. So truly, when we say we want to find the irreducible representations R, what we mean is we want to find the representation maps, which are the images of the elements in the group, the group that we're considering under the representation. And this, in particular, fully specifies the representation itself. So I'm going to use a kind of trick, you could say, which perhaps at first doesn't seem quite natural, but once you've seen it at least once, I think it becomes quite natural. So as I told you, I want to determine the representation maps. So I want to find R of G for any G in the cyclic group. And I'm going to start by considering R of 1. And in particular, I'm going to consider R of 1 to the exponent n. So if you try to visualize this, R of 1 to the exponent n is just R of 1 times R of 1 times R of 1 n times. And if I start with the simple case n is equal to 2, then I'm considering R of 1 times R of 1. Now remember that R is a group homomorphism. So if I go back to my group homomorphism property here, we know that R of 1 times R of 1 is equal to R of 1 times 1. Now, if I move on to n is equal to 3, I'm considering R of 1 times R of 1 times R of 1. We already know that R of 1 times R of 1 is R of 1 times 1, and if I now apply again my group homomorphism property, I will find that R of 1 to the exponent 3 is equal to R of 1 times 1 times 1. And now if you successively apply your group homomorphism property, what you find in the end is that R of 1 to the exponent n is equal to R of 1 times 1 times 1 times 1 n times. And now we just use the notation that 1 times 1 times 1 n times is 1 to the exponent n. Although careful here, this is just notation, but remember that, so this is not 1 to the exponent n, like multiplying 1 n times, because this would just be 1. Here, 1 to the exponent n is just a shorthand notation for 1 times 1 times 1, where the group law is, in this case, addition mod n. So it's not necessarily multiplication. And so if we apply the group law, 1 to the exponent n is equal to 1 times 1 times 1 n times. So it's equal to 1 plus 1 plus 1 n times mod n. And 1 plus 1 plus 1, this is just n mod n. So if you remember, n mod n I told you is 0. So 1 to the exponent n is 0. So what we found is that R of 1 to the exponent n is R of 0. And now it follows from the group homomorphism property that any group homomorphism maps the neutral element of your initial group to the neutral element of your final group. And here, in our specific case, the neutral element of the cyclic group is 0, and the neutral element of GL of C, so the invertible linear maps acting on the complex numbers, is 1. So R of 0 is equal to 1. So what we found is that R of 1 to the exponent n is equal to 1. And this just means that R of 1 is an nth root of unity. An nth root of unity is just a number such that if we take it to the power n, then we get 1. And there are n nth roots of unity for any n equals 1, 2, 3, etc. And because there are n nth roots of unity, we will label each nth roots of unity, so each solution to the equation R of 1 to the exponent n is equal to 1 by some number q, which goes from 0 to n minus 1, so that there are indeed n nth roots of unity. And now the general expression for an nth root of unity is e minus 2 pi I q divided by n, for any q from 0 to n minus 1. So we have found that the representation maps acting on 1 are RQ of 1, so Q labels which representation map we're talking about. RQ of 1 is equal to E minus 2 pi Q divided by N for any Q from 0 to N minus 1. And now remember that what I'm interested in is R of G for any G in the cyclic group, not just 1. And I'm going to again use a trick similar to the one I used in the blue box. So R of G, you can write G as the sum 1 plus 1 plus 1 G times. And by definition of the group law, 1 plus 1 plus 1 plus 1 G times is just 1 times 1 times 1 times 1, which we denote by 1 to the exponent G. And if we now apply again our group homomorphism property like we did in the blue box, what we find is that R of g, which is equal to r of 1 to the exponent g, is equal to r of 1, the whole thing, to the exponent g. But now, we did determine what r of 1 is, and so we just need to take this to the exponent g, and we find that rq of g, for any g in your cyclic group, is equal to e minus 2 pi I q g divided by n for any number q, which is equal to 0 until n minus 1. So here we have found the representation maps for the representation of the irreducible representations of the cyclic group on the complex numbers. So now we know exactly how our cyclic group acts on the vector space of the complex numbers. Our irreducible representations RQ take an element small g in the cyclic group, and they associate the linear maps RQ of g, which are just e minus 2 pi qg divided by n. Here they are just numbers, and so the way they act on the complex numbers is that they take a complex number z and they just multiply it by rq of g. So what we get in the end is z times e minus 2 pi qg divided by n. And to just finish on why we would be interested in knowing how the cyclic groups act on the complex numbers, if we have a system and we observe that this system has a symmetry whose associated group is the cyclic group, then in order to explain the experiments, to construct our physical theory, we want our physical theory to be invariant under so we want our physical theory to have the symmetry associated to the cyclic group Zn. And so remember, in order to know how we can construct our physical theory, which is invariant under the specific symmetry that we're considering here, we need to know how our cyclic group acts on vector spaces, such as, for example, the vector space of the complex numbers, which we know now exactly since we know the representation maps. And I'm going to end on this. So thank you very much, everyone, for listening. And of course, I'm very happy if ever you had some questions to answer your questions.